And somehow they don't play symmetrical roles. Like, for instance, a positive class is a fraudulent credit card transaction. There are hopefully a lot less fraudulent transactions than real transactions, but their cost is not the same at all. A positive class can define a relevant document for a particular query. Just say you want to classify documents for a particular query, and you want to find the relevant ones. So it's going to be a small number of documents in a sea of negative. And you have the pacemaker problem that I like to take. I got this example from Marwan Jabri, that's a long time ago. And he used to work on having little adaptive systems in pacemaker that decide whether to send an electric shock to the patient or not. So you have a sensor, senses what the heart is doing. And if the heart is doing something strange, well, you send electric shocks in rhythm in the hope of trying to put it back on schedule. And of course, this is not very comfortable to have electric shocks. At least with the pacemakers of that time, it was certainly not comfortable. So that's a positive. And so if you do a false positive, that you send an electric shock, you're going to create discomfort for the patient that's not needed. If you do a non-detection, let's say a false negative, so basically the heart is doing something strange, and you're not sending an electric shock, it's probably going to be very bad for the patient. And so you have different kinds of error. False positive, false detection, false alarm is usually more expensive. False negative is, well, actually, false positive is usually acceptable. False negative is not acceptable. And the difficulty is that the cost of these things are difficult to estimate. Like, go back to the pacemaker example. If you're the patient and people ask you what you do, what you prefer, you're going to say, well, I would like to be biased towards false positives because I prefer to receive electric shocks once in a while than to die. But if you're the maker of the pacemaker, the problem is that when people receive an electric shock for no reason, they complain. If they don't receive an electric shock when they should, they don't complain. So the point of view of the builders of the pacemaker is slightly different. And of course, the balance is difficult to strike somehow. You know, it's not that simple. So let's define two probabilities. The probability of non-detection, so I have a classifier f, is the probability that f of x is less than 0 when the class is +1. That's a false negative. And the probability of false alarm is the probability of f of x greater than 0 when y equal -1. That's a false positive. And the standard way to deal with this is to have two costs. A positive cost times the probability of non-detection, plus a negative cost times the probability of false alarm. And say, well, we have to find these costs right and correctly, and then we optimize this function, and then we have a nice solution. Now, as I explained before, these costs are difficult to find. And also, they're dependent on things that are rare. Like, for instance, suppose you take a fraud detection problem. It turns out that the amount of fraud at a given time is not constant. It's going to move widely. Sometimes you're going to have 1% fraud, sometimes 10%. And if you have a cost that's global, how are you going to decide what's the cost of fraud? It's very annoying.
Does the fact that you are also, I mean, it's kind of like a feedback system, because you're detecting, if you were detecting fraud, that's going to also influence the distribution.
Yeah, you have that as well. But I'm not even discussing that at this point. I'm just discussing that finding the C+ and C- that makes sense, that you can make an argument that they're correct, like saying that putting a cost on a false positive or a false negative for the pacemaker problem, it really depends on the point of view you have, you know. So there is a solution that's standard in statistics, is Neyman-Pearson Classification. So instead of defining two costs, it's often more practical to define a limit on the probability of false alarm. You say it wants to be less than a certain value rho, and to minimize the probability of non-detection. You say, well, you want your pacemaker to give electric shocks for no reason in less than 1% of the cases. And given that constraint, try to maximize the survival of the patient. It's just easier to argue. And in fact, these two methods, they share the same solution. They're not that different, because if you take a function that's probability of y equal +1 given x, I call that the optimal ranking function, because if you rank the example, that's the best way. You can show that if you compute a threshold correctly, the optimum of the asymmetric cost, in fact, the best, you can implement the best asymmetric cost classification by doing P of y given x minus some threshold. And you can do the best Neyman-Pearson classification doing R star of x minus some threshold as well. That's just a bit more complicated. So we're really discussing about the same space of solutions. It's just a different way to express it that can be more convenient. So one thing we can do, and that happens a lot in practice, is to say, well, we build a classifier with some method, with data that's reasonable, and then we adjust the decision threshold. So your classifier is now fb of x, which is f of x that you obtain by some data set. You do some trick. It's fixed now, and you just adjust the threshold. And you can define the probability of true positives, which is p of f of x minus b greater than 0, given that it's a positive, which is the same as 1 minus probability of non-detection, and the probability of false positives. And if you look at these probabilities, when you change the threshold, if the threshold is low, you're going to say that everything is a positive. So the probability of both things is nearly 1. If the threshold is high, the probability is going to be... Can we see really the yellow thing there? I don't know. Maybe I should make it darker. Yeah, OK. It's going to go for now. So for B, very small is close to 1. For B, very high is close to 1. And you, of course, hope that the probability of false positive decreases faster than the probability of false negative. So you have these two curves like this in that space. Now, the interesting thing is that if you take a particular point here and measure these two distances and plot them in a different set of axes where you have the probability of false positive and probability of false negative here, you get, when you go over these curves, you describe something like this, and that's the ROC curve. That's the receiver operating curve. So there is a connection between these two aspects, and you can actually push it further and understand how you can optimize the error under the AUC and everything. So, OK, so this explains the connection between these two probabilities and the ROC curve and how they work. But we would like to do more. We don't want to just learn a threshold. We would like to learn a complete classifier to do the Neyman-Pearson thing. Because computing a classifier for some way that's optimized for a different point on the ROC curve and then tweaking it by adjusting the threshold is obviously non-optimum. So the first problem you have is that the probability of non-detection and false alarm, they're defined asymptotically. So you have to take the empirical counterparts. So the probability of non-detection empirical is 1 over your number of positive, sum over all the positive of an indicator function of f of xi less than 0. So basically, it's the count divided, it's the count of, actually, it's the count of non-detection divided by the number of positive. And the other one is the count of false positive, false alarms, divided by the number of negatives. So they just count. And now you can write the Neyman-Pearson problem as being the minimum of the empirical counterpart of PMD, subject to the constraint of the probability of false alarm, empirical. Now the problem is that this counting function, these step functions, the indicator of f of x greater than 0 or less than 0, they're not fun to optimize. Just there is nothing to optimize there. You want to make them look better. So we use a standard trick. We replace the step function by a little sigmoid. And you write the same function, but you replace the step function here by these sigmoids here. So now you have a smooth function. something you can optimize. It has a gradient. So we like that they have gradients. And you can write an empirical form of the Neyman-Pearson problem, minimum of this smoothed probability of non-detection subject to the smooth probability of false alarm, less than rho. And you can add a regularization term if you want. And all this, there are some studies showing that this is actually reasonable, except that you have a non-convex objective function with non-convex constraints. And that looks bad. Except that sometimes it's good not to know that it looks bad, because it's not that bad. They're non-convex, but they're not so badly behaved. So let's suppose we don't know that this is bad. And go. So we have a non-convex optimization with constraints. So I'm going to write a Lagrangian. So you might have seen Lagrangians only in the case of convex optimization. And it's often underappreciated that they mean something also in the case of non-convex. In fact, when you have convexity, you have two kinds of properties. One property is that you can characterize that there is the minimum pretty well. There is a single minimum or a single minimum space that's convex as well. And the convexity comes with some regularity consequences. If something is convex, then you have continuity properties, and you have subgradients, and you can do some calculations using that. Here, we're not going to have the first one, because it's not convex. We can have many minima. But we can assume smoothness, because this is what we did. We changed the step function into something smooth and continuous, so we have differentiability. And that's actually enough to make the Lagrangian trick work. And there are some nice results that are actually useful in non-convex setup. First, a local saddle point of the Lagrangian is a feasible local minima of my problem. And conversely, if I assume that my cost function, my constraints are both differentiable, I assume I have the Caron-Kuntuscher qualification conditions, then I have the converse. Feasible local minima of the constraint problem are critical points of the Lagrangian. So my problem in that setup reduces to finding saddle points in the Lagrangian. How to do that? Well, there is a standard algorithm for that. It's called the Uzawa algorithm. So what the Uzawa algorithm does, it says, well, I want a saddle point of the Lagrangian. Well, I'm going to fix mu, the Lagrange coefficient. I'm going to minimize for this mu and find some f function. And then I'm going to see if my f satisfies my constraints by looking at the gradient of the Lagrangian with respect to the Lagrange parameter. And I'm going to do a coordinate ascent, actually a gradient ascent in that direction. It's a coordinate ascent because there is a single one in that case. Now, the convergence of this is not really obvious because the f star mu, which is the minimum of the Lagrangian for a fixed mu, so that can be a non-continuous function. But in our particular case, because there is a single constraint and because it's pretty simple, we can show that the probability of false alarm of the optimal solution for fixed mu is going to be a non-increasing function of mu, if you don't do things too stupidly. And I can go over with details if you want. So that means that basically, you get a kind of simple feedback. You optimize for a particular mu. You look whether you're in the constraint or not. If your probability of false alarm is above the constraint, you're going to increase mu by a little multiplicative factor so that next time you do the optimization, you get something that's more constrained in that respect. So you have to look at the Lagrangian to understand it. So I have this. The mu part tells me whether the constraint is satisfied or not. I fix mu, and I optimize. I find the f star. I look at my constraint, and am I above mu? Above rho, sorry. If my probability of false alarm is above rho, well, let's scale mu higher a little bit, and do it again. And then next time it's going to be slower. It's going to be lower, sorry. If it's too low, I can reduce mu a little bit, and next time it's going to be higher. And after a while, I'm going to get there. So We can do that, but it's not very fast because you have to optimize your Lagrangian for fixed mu, and then you have to adjust mu and everything. So you could optimize with a stochastic algorithm, and I'm going to give some results about that, but it's not super fast. But what you can do is do it in a stochastic fashion. So before I'm going to say something. Suppose mu is fixed. What do you have here? Both the probability of non-detection and probability of false alarm, they're sums of sigmoids times the output of my classifier, multiplied by y and so on. So all this sum, probability of non-detection plus mu probability of false alarm and everything, they can be a sum of the usual classification criteria with strange weighting. So what mu is doing is that it reweights the positive and the negative in a different way, in a way that's going to be adapted to try to hit the constraint. So let's get a stochastic version of that. So the idea is that you want to do a gradient descent in the W variables, and you want to do a gradient ascent in the mu variable. So we set initial value for the function in mu. We choose decreasing gains gamma t for the W part, and you choose a very small gain, has to be very small, for the mu part. So you pick a random tuning example, xt, yt. I forget about the at for now. And what you do is that you perform your update. So W becomes 1 minus gamma t lambda W because of the regularization term, minus gamma t the gain. At is a little trick that includes the mu, and the derivative of your sigmoid. And the sigma prime is another weighting factor. And then, if yi equal minus 1, if you have a negative, you compute the derivative of the Lagrangian with respect to mu, and you make a multiplicative update on the basis of that, with the idea to do a gradient ascent. So you have a gradient descent in W, a gradient ascent in mu. So the AT is there. The AT are these coefficients. I told you before that if you look at the Lagrangian and write the two probability of false alarm and probability of non-detection as a sum of sigmoids, you get different weighting factors. So the weighting factors are these. For the positive, it's going to be n over n plus. And for the negative, it's going to be mu n over n minus. Fine. Now, convergence of this. Well, this is not a gradient descent. We look for a saddle point, not a minimum. We do this gradient descent in W, this gradient ascent in mu. So it's another theory, and the good news is that it's been well developed as well. In the stochastic approximation literature, you have extensive studies of this kind of saddle point search problems, precisely because that's the way to do constraint optimization with stochastic gradient. They're just even more complicated than the standard gradient stuff. It's just hell. But the same kind of result apply, basically that you have convergence at a mild condition, that the speed is more difficult to come by, but it's not catastrophic, and everything and everything. So let's now consider that we have an imbalanced data set where we have very few positives and a lot of negatives. That's a bit annoying. What we could do is instead to draw positive and negative. So you have a pool of positive, a pool of negative, and you're going to draw. I draw a negative, I do my stochastic step. I draw a positive, I do my stochastic step. I draw a negative, I do my stochastic step. I draw a positive, I do my stochastic step. So is it going to change the result? And the curious answer is no, it's not. Because my two probabilities, the probability of false alarm and the probability of non-detection, they define according to the conditional probability given the class. So the problem, the Neyman-Pearson problem of minimizing the probability of non-detection subject to a constraint on the probability of false alarm is defined independently of the proportions of positive or negative. Because the probability of non-detection is something that's basically among all the positives, how many are not detected? So that's something that doesn't depend on the total number of positives. It's something that depends on the proportion among the positive. And the probability of false alarm is among all the negatives, how many are false alarms? And I want that to be less than rho. And that's defined independently of the number of negatives. So if I rebalance, I don't change the problem. And the way it's going to work is that if you look at the Lagrangian here, you see that the two terms, probability of non-detection and probability of false alarm, they're connected by this mu factor that's going to be adapted. We're going to adapt mu to ensure the probability of false alarm is less than rho, which is predefined. So if you optimize that way, it's just going to work. You can change, rebalance the positive and the negative with that formulation, and it's going to work. And if you rebalance positive and negative, you're going to go a lot faster empirically. Now you can make some improvements. You can change the initial value of mu to reflect that you're modified, or you can redefine the AT and rebalance it so that you get a similar effect. But that's a detail. The important point is to understand that if you take this algorithm and present the positive and the negative with different proportions, so you oversample the positive and undersample the negative, it's not going to change the result. The only thing is going to change is the mu that you're going to find at the end. Does it make sense? So let's look at some results. Well, so Pageblocks is one of these UCI datasets. It's interesting because it has basically 10% positives. It's a linear model. I don't see anything on my screen, and I cannot point on the other one. It's a bit annoying. Let's see. Is there an on-off button there? No. No way. So we use 50% training set, 25% validation set because you have to adjust the various regularization coefficient, 25% test set. So let's look first. That's the target probability of false alarm, and that's the actual false alarm. And we compare a bunch of algorithms. There is the online Neyman-Pearson SVM because it means it's linear with L2 regularization. That's the stochastic algorithm I just described. The BNP SVM is just the Uzawa algorithm with a couple tricks to make it faster. The AC SVM is an asymmetric cost SVM, C plus, C minus. And there is this paper, Davenport 2010, that describes a nice way to do the cross-validation to do it fast. And in addition, you can tweak the code and as a SVM solver, instead of using the standard stuff, you put a stochastic gradient. So the SVM solver itself is fast. There is a generative method that, well, I don't really like it. It's more in the statistical tradition where you define a generative model and then you try to fit it and do things like that. And there is another algorithm called SVM-perf that's a variant of the structured SVM. And what it does is that it optimizes a convex upper bound of a cost function that's defined as a function of the numbers that you have in a confusion matrix. So it's a bit of a hairy algorithm. So if you look at the target probability of false alarm versus the one you observe, you see that the Gen algorithm doesn't work. It gives you a probability of false alarm that's way below. It's way too conservative. And as a result, when you look at the probability of non-detection, it's way above. It's a bit sad. The SVM-perf, it works quite well. But for very low probability of false alarm, it starts to be off. And the reason is that this trick of optimizing a convex upper bound of what you actually want to optimize. When you start to push too hard on the target PFA, it seems to hit you. I don't know exactly what is the mechanism that does it, but it's a constant thing with, we can verify that this algorithm optimizes what it's supposed to optimize, but when you want a very low target PFA, it's off. And the other algorithms are pretty much on target. Basically, they get the probability of false alarm we want. Now, if you look at the probability of non-detection, you can see that they're pretty much similar because it's the same kind of model after all. except for those algorithms that have deficiency in the probability of false alarm, where when the deficiency happens, you get different things, of course. Like, well, okay. And finally, this is the target PFA and the time. And you see that the asymmetric cost SVM on such a data set is pretty much constant because it's dominated by the search of the C plus, C minus that you have to search by some kind of cross-validation. Here at the bottom, you have the online NP SVM that works. You have the generative algorithm that doesn't work. And you have SVM perf that works quite well. One of the things to understand, and that's been studied by a paper by Francis Bach quite a while ago, that if you do C plus, C minus in a SVM, so you take the hinge loss and you weigh them by two different slopes of the hinges for the positive and negative. The C plus and C minus that you have to apply on the hinge is not the same as the C plus, C minus you have in the cost function. Because in the cost function, you don't have a convex thing. You have ideally a step function. And because you use a convex approximation, when you start to be asking for very small probability of false alarm, for instance, that's going to start to hit you. And you have to balance, and you find that the optimal C plus, C minus that you have to put in your algorithm is not the same as the one you specified at the beginning. Well, if you do it with the non-convex approach that's described here, you don't have this problem. Basically, we can verify that the C plus, C minus that we have at the end, which we find because of the mu and because in the Lagrangian you can see the two terms and you can see what are the weighting factors, they're pretty much on target. So you have less cross-validation to do, less search to do. But that was a relatively small problem. Let's take a bigger one. So it's the Covertype data set. So this time we have 200,000 negatives, 20,000 positive, still linear. And what do we have here? We still have that the generative model doesn't work. The online SVM is still on target. And the AC SVM, the asymmetric cost SVM, well, sometimes it starts to be off a little bit. And that's also because it doesn't find the C plus, C minus. So this algorithm has a sophisticated way to try to find the C plus, C minus in an efficient way. And sometimes it's a bit over conservative, but it's not that bad. So again, the probability of non-detection, they're pretty much the same because it's the same model, except for the generative model that's completely off because it's off here as well. And if you look at the time, you see that the online approach is a bit faster than the AC SVM. So now you have to understand that in this asymmetric cost SVM, we kept the code that searched for the C plus, C minus, but we replaced the solver by a stochastic solver that's very fast. But we replace it by the new one that's linear, the C, and that's compared to SGD. So this difference of 10 to 15 seconds, basically, that's the time to search for C plus and C minus. In the case where you do the non-convex stuff, the search space is more limited. You have to search for the lambda of the regularizer, and that's it. If you do the asymmetric cost SVM, you have to search both, because if you want to hit a particular objective in terms of positive and negative cost, the ones that you have to put in your algorithm are not the same. That's the price of trying to be convex. There is another graph. It's actually the same data, but the thing is that I plotted the SVM perf as well. And you see SVM perf on this data works quite well in terms of whether the probability of false alarm is on target. It's actually worse. Probability of non-detection is higher. And it's orders of magnitude slower. That this structured approach where you look at the confidence matrix and look at all the possible values of the confidence matrix, define a cost function on this, it's very effective. And there was a very nice work to make it work on a small data set, where the speed was very nice. But when the data set becomes large, it's just explosive. It's something in, it scales like the 4th to 5th exponent of n. So it's like n to the 4th or n to the 5th. So when n increases, it's gone. While this one scales like n. It's the stochastic method.
Are there any comparisons to the non-optimal approach of just training symmetrically and taking a threshold?
Training asymmetrically and using?
I don't know, is there any comparisons to the non-optimal, the idea where you actually don't do the asymmetric cost, just do the train standardly and just pick the threshold? The approach you mentioned first, that we kind of said, well, this isn't optimal, has that been compared to?
Just as using the threshold. I have it somewhere, but not here. If you look in terms of ROC curves, you can see that you can, for instance, target the point of the ROC curve with a fixed classifier, and then you adjust the threshold to move against the ROC curve. And what you see are things like this. So if you plot, so this is the ROC curve you could get by using this for various values of rho. That's the one we believe is optimal. Now suppose you take a point like this, and you adjust just the threshold. You get something like this. So in the vicinity, it's good, and when you go far away, it becomes worse. So there is so we have a nice drawing that tries to show this kind of things. And so you target a point, and you try to move away from the point by just adjusting the threshold. This is less good than targeting the new point you want. So, OK, you could target the point you want. There's an extension of this. It's a proteomics, so let me describe the problem. You have some biological soup. You want to know what's inside. What kind of proteins are inside. So a procedure that's cost-effective, but not always very accurate, is to first break the proteins to peptides. And then you put this into a separation column that's going to separate by various physical properties. And you send the thing slowly into a mass spectrometer. And you get a collection of spectra that represent the various things that are in the solution. Now, you get a lot of spectra, like 100,000, something like that. And then you take the spectra and you match them against a dictionary of spectra for non-peptides. And you get a lot of matches. And some of these matches are good, and some of these matches are completely crazy because the spectrum can be very noisy. You could have, I don't know, a piece of dust. Something didn't work well in the mass spectrometer, so you get a lot of noise. So you have all these matches. You don't know which ones are good or bad. So the procedure that they use is to augment the dictionary with fake peptides. They call them the decoys. So now you have a dictionary that are real peptides and plenty of fake peptides. And when you have matches, you can match the real peptides, and you don't know if it's a positive or negative. Or you can match the fake peptide, and you know it's a negative, because they don't exist in nature, these things. That's just a fake stuff. So you get a problem where you have negatives, and you're sure they're negatives, and you have positives, and you're not sure. And what you would like to do is find some positives that are worth more experiments. So if you suspect that there is a certain protein, you can design experiments in a wet lab to prove that. That's a lot more costly. So you would like to screen all your matches to find those that are worth examining. So what we would like to do is construct a classifier that returns as many good matches as possible, subject to a constraint on the proportion of decoys. That's called the Q value. So, OK. Let's write that. You want to minimize the probability of non-detection, which means maximize the probability of return positives, subject to a constraint that says that the number of false alarm is less than Q times the number of positive returned by the system. That's my constraint. And it's very similar to the Neyman-Pearson problem. And you can use exactly the same techniques. You write the Lagrangian. You think about the Uzawa algorithm, but you actually don't do it. You write a stochastic approximation of it. And the results are that you take something where you have 70,000 matches that are called true, but in fact you don't know if they're true or not. 70,000 matches to decoy peptides that you know are negative. And I compare this to a model that was a ranking model that was state-of-the-art called QRanker. And using exactly the same model. In that case, it's a small neural network with 5 hidden units, nothing very complicated. What you see is that if you do it this way, for the small value of the Q value, which means if you want to be very sure about your positive, you return slightly more positives. So you have slightly more sensibility to what you see. But it doesn't say much because we don't know if they're positive or not. It's just that it's going to give you more candidates with less non-negative. Or if you fix the proportion of non-negatives, it's going to give you more candidates. To actually know whether this is good or not, you have various things you can do. The ultimate thing is actually to say, well, this means that this protein might be present in that soup. So I'm going to design a wet lab experiment to try to verify it and then try to think what it means. That's costly. You have other things you can do. That was the work of Marina Spivak, is that you can use other methods to find proteins and try to see how many of these extra proteins you find are non-proteins for that soup out of other methods. And it's not easy because this kind of method is a lot more sensitive than pretty much anything else. But by observing that in the extra proteins you find with this, there are a number of ones that you know are present. So basically you get some real positives. Then you can have confidence that this is good. But anyway, that's a progress. And that's pretty much all I have. I'm sorry to be a little bit fast this time again. Maybe I can answer questions? Yes?
In the case where you have equal costs, does it reduce to something like simple?
In the case where you have equal costs?
Where you have imbalanced classes, but the cost is, so it's not this case where a false negative is catastrophic, but it's equal costs.
Oh, well, it works just the same, except that when you have very imbalanced classes, suppose you have less than 1% positive, and the cost of false alarm and non-detection is the same, you can get 99% accuracy by saying that everything is negative. So usually, with imbalance comes the concern that the cost is going to be asymmetric. Otherwise, you can just ignore the imbalance and just ignore the positive. So they go hand to hand, typically. Well, you get an early break. I don't have anything else ready. Oh, more questions, sure. No questions? Okay, well, thank you very much.